any major one. But in case of MV, we have different issues. Like they have two options. Like one is armoring of the cables, and the other one is the sheath, which is copper or aluminum one sheath of the MV cables. So if we see that, if we see that the armoring and sheath, they are conductive materials. Okay. So when the residual current and other thing will travel in the sheath at the joint point, at the joint point, they should be properly bounded and other things. So we have faced a lot of issue in our uh, execution project at that phase like 1 month ago. Our MV cable should MV cable sheath and armoring should be burned at the site when they start the cables. And when our team has analyzed that, what is the main issue in the MV cables, why they are armoring and sheath should be uh, burning. So in that case, because we are working in the South Africa region, in that case, as per the ESCOM standards, ESCOM basically they are a uh, grid company, ESCOM. As per their standard, we have to bound the cables, double bound. Double bound mean both side of the cables should be armoring and sheath should be earthed. And when they analyze our team, basically, yes, Mr. Kazi?
Sir, actually, where the MB cables are used in the system?
Oh, yeah, okay. Okay. Basically, uh, I have just like one class ago, I have explained that the voltage difference 1 minute ago, 1 minute, Amar. I have explained that the 400 volt, then 11 kV, then 33 kV, and then 132 and other things I have explained in previous lectures. And I explained that the 400 is basically the LV side. Then 11, 33, they are the 15 kV, 22 kV, they are the MV, medium voltage. And then 132, 66, 240, they are in the high voltage sides. So, what is the difference? Basically, uh, when the uh, the the voltage is low, the voltage is low, the current is high. The current is high. So, when we have to travel or to transfer the power, the energy, the electricity, basically transfer the electricity from one side to another side in some simple way we would talk about. So, if we have to transfer that energy, like we have grid station where the electricity generation is possible, and we have to give that energy to the different villages and other things. So what we have to do, if we do that process in low voltage 400 volts, what will be happen? Because the voltage is low, the current will be high because they are inversely proportional to each other. So the current is high, so the losses in the power losses should be on the higher side. So that is why we have to minimize that one. We will increase the voltage level and decrease the current, and we increase the voltage from 400 to 11 kV, 22 kV, 33 kV, and minimize the power losses. And when we reach out near to that village or any location, we again use the step up, step down transformer, because the transformer working is that they will take the low voltage in one primary side and step up or step down. So they are doing both the work. So near that one, we will again step down the voltage and increase the current. So another question will be generated. I'm just again, if you don't know about that, why we are again doing to the 400 volts? Because our systems, electricity appliances, like they are working on the 400 volts. They not capable to withstand the voltage up to 11 kV and other things. Industrial level, they have the capability, like motors, they have 11 kV voltage level, but in the home appliances, low voltage. So we have to decrease and step down the voltage. So why we use MV cable? So to transfer that power from one point where the electricity is generating to the another point where we have to transfer that energy, like use the electricity. So in between, to travel that power, the path should be called the cables. And the voltage level, what is the voltage? Basically, from energy grid station where they are the power is generating. Here the voltage we have step up from 400 to 11 kV or 33 kV. And now the output power should be, the cable should withstand that voltage 33. So that is why they are called the MV cable. And if the cable will withstand and travel the power of the 400 volt, they are called LV cables. So that is a just difference. That is why I just want to explain you in brief. I think it's more clear to you.
Yes, sir. It's clear. But in the solar system, this part actually it's not light on us. Actually, the utility or who actually supply the power to the factory, and they do these stuffs, isn't it?
Uh, uh, can you give me some answer regarding your company? You are just working on the residential side, a commercial side, or you are working on the large scale project? Can you give me that one answer?
Yes, yes, yes. We worked both side, and I don't have that much experience in this field, and that's why I'm in this course. And as far as I've seen that, um, I we just bring the wire till the meter. The
Yes. Okay. I just uh, get your point now. So basically, you are just working up to the energy level, energy meters. So you are just installing the solar power plant and the rooftops. Then you will install the inverters and small DB, in which one, two, or three the breakers you will use are installed equal to the number of inverters, and then you will install one output breakers, and you just connect that cables to the main DB of the client. Okay, so
yes,
you are
yes,
just, so you are just doing the residential side or commercial side at the low voltage levels. So the cable just use between your inverter output to the DB where we are using, or from the DB to the uh, client DB. Two cables you are using, and the other cable you are using from the rooftop to the inverter. Basically, from the rooftop to inverter, they are DC string cables, and then from the inverter to the your sub DB distribution box where we you are installing the breakers. They are called the LVAC cables, and from that main output cables from the client distribution boards, they are called the LVAC. So you are using just small cables, and you have to, if you have to analyze that cables, you have to size properly. But at residential level, it is not a too much big issue. But if we you are working in the future, when you expand your company and you will working in the large scale project or in industrial level, where you have to terminate your system on the DB where the system voltage should be 11 kV or 33 kV. So you have, maybe you have to terminate your system on that level. So in that case, you have to use the MV cables, you have to use the transformer and other things. Okay.
Okay, sir. Thank you. I got it.
Okay. Okay, thank you. Yes, Amar, now it's your turn.
सर जो हमारी एमवी केबल्स होती हैं इनकी रेंज जो है 1 केवी से लेके एज पर आईईसी 36 केवी तक होती है।
नो नो, एलवी केबल बेसिकली जो होती है ना
नो,
आपकी,
एमवी एमवी
एमवी
केबल,
केबल,
एमवी केबल।
एमवी केबल बेसिकली they are just like above the above 6 kV. I think above 6 it should be called MV cables. I have to clear, but mostly will be used as the 11 kV, 22 kV, 15 kV, and 33 kV. Okay, up to 3.3 kV. Mostly when you are using in the large scale project, the megawatt scale project, you have to use the 300 kilowatt, 400 kilowatt inverters. So you have to use the large cables like 300, 400, 500 cables, and their voltage level should be 3 kV or 33 3.3 kV. 3.6 is the maximum cable voltage. So they are in lie in LV sides, not on the MV side. So MV should be like 11, 10, 15, 22. They are the range. 33, they are the MV ranges.
सर उसमें अगर हम एमवी केबल्स यूज कर रहे हैं लार्ज स्केल प्रोजेक्ट के लिए तो उसमें हम सिंगल कोर यूज करेंगे या 3 कोर यूज करेंगे केबल।
Basically, it is depend upon the cable vendor. Mostly, which I have seen in my experience, up to the 185 240, we use three core cables for the MV. But above that one, we shift to the single core because the MV cable should be very heavy cables. Their bending radius should be on the higher side. The outer dia of the cables should be too much large scale, too much large. So that is why we have on-site handling is very difficult. So we should shift to the single core. But you can use both. But three core mostly for the small level, like 120, 185, 150, 240, up to maximum by 240, you can use a three core. Above that, you have to shift to the single core. Okay.
यस सर, ओके।
Okay. So I'm just sharing my screen and I have just showed to one things on the Google. Then we should move to our systems. Uh, Basically, I want to show you something on the Google that is basically the cross bonding, double bonding, and other things. I want to show you on the cables bondings. Mostly when you will use in the large scale project, maybe you need that one, but at that time you just know the things. What is that basically? Okay, okay, we will discuss this matter with by tomorrow class in the detail on the thermal assessment. At that time, I think we should just explain. I will explain the Excel. Then tomorrow we have the thermal assessment class in which I need this information to share to you, to all of you. Then we will discuss this matter. Okay? Because I have to just collect the data. Then we will discuss in the detail. So basically, this is the MB cable sizing sheet I have prepared. First of all, I have just explained to all of you that in case of MV, in case of LVDC, DC string, and LVAC, we just go to the derating factor and then the voltage drop criteria. But in case of MV cables, we have different issues. MV is very difficult cable sizing. Um, First of all, we have to analyze the short circuit study or short circuit criteria on which basis we have to size our cable. First of all, we have to check that our cable, what is the basically size as per the maximum fault current. Maximum fault current. What is basically the criteria? So here I just show you, I have that is the system voltage operating like 33 kV, and this is the transformer rating. Because we have to consider the transformer rating for which we are sizing our cables. Okay, so our transformer size is 7168 kVA at 40-degree temperature, and current RME stations. So we have to use that one, like 33 kV under square root. That is the maximum current at 40-degree temperature. That is the basically the formula. P is equal to square root of 3 VI. So we have V that, okay, we have that power. So we should get this current. Current basically current I is equal to P divided by square root of 3 multiply with the voltage. So I have just applied this formula and calculate the current. So you should see that in case of when we compare to the LV cable, LV current, they are too much low. In the previous day, we have just sized the cables at 254, 300 uh, ampere in case of LV. Now, in case of MV, the voltage is higher, the current is lower. So, we have calculated this current. Now, we have to this fault current. So, where we get this fault level? Fault level basically, we have to check that if our system go into the fault conditions and their maximum current should be what is the maximum current? Okay, the maximum current should be that will follow from like main transformer, the main output substation transformer. The current will flow to the MV cables and other cables, and they will damage. Like they will maybe it will travel up to the 1 second, 0.5 seconds. So we have considered when we size it for 1 second, or it should be for the 1.5 second. So this where we get this fault level, fault current. It is basically we get from the fault current study, or we get from the main transformer maximum current at Z impedance. Okay. So basically we have considered 25 kA kilo ampere for the 0.5 second. Okay. So this is formula as basically the conductor size, I fault, and square root of T, this temperature, time divided by K. Basically, K is the value we get from we get from the IEC standard. We get from the IEC standard. I will send that IEC standard in the group, and I will also share this calculation in the group. Okay, how we will calculate this fault current. If we don't have any current study, We have to just know how we will calculate that fault current and we will perform our MV cable sizing. So that is why I will share these things in the group. So here you can see that at this fault level, our size should be 208. So our cable size, minimum size should be 208. So we have to size our cable greater than 208 because in the market only the 240 size is available, uh, higher than this. Because the lower is 185, so we don't use that one. So we have to use 240 cable here. And then the active power, it is the client requirement, they will provide us. So here is the same one. Like we have considered the derating depth, resistivity, ground temperature, and other things, grouping factor like the same one, which I have already explained to all of you. But for the MV, we have to use the IC standard or vendor data. So we have to use the vendor data or we have to use the same one like uh, the IC standard. And then this is the total derating factors which are as per this grouping factors because we have this above one the factors and then we have decided these factors on that basis. Okay. Now, now what we will do just this is mentioned that because in case of MV transformer, in case of MV transformer, I will show you like MV sizing. Like I don't have any specific MV layout. Okay, okay, okay. Basically, basically, I will share some layout, short screen layouts in the group for your information in case of MV. Basically, when we are doing the MV cable sizing, we have to do just so we have to loop in, loop out cable MV transformers. I will just search on the Google if they find any block diagram. Google MV transformer. In- Here you can see that. Here you can see that we have transformer that one like this one. This is the supply power. Like you can see that this transformer is input, then it go output, then their output is going to the input of that transformer, and then their output is going to the input of that transformer, and then their output is going to the input of that transformer, and then output is going to that one. Like they have like six transformer in one loop, six transformer in one loop. So here, this is the output current of one transformer, like 125, which we have already calculated. So here in that cable, if we, if I will show you, like if we see that we have this transformer like loop in, loop out. So if their transfer is this transformer output current is 125. So when this cable like from this one, if we see that this is the output cable and this transformer output current, maximum output current is 125. So in that cable it will travel, what is the current will travel through that cable? It should be 125. Now when this cable is in into that transformer and out that transformer, so here two transformer will be connected in series, in parallel, sorry, in parallel. So what will do? Their current will be add up. Now in that cable, the current should be 250 ampere. Now here again 125 is added in that cable. So in that L3 cables, it should be traveling 375. And then this is the L2 cables. So in that cable, it's become 500. And then in L1, it should become 625 ampere, like same one. So you have see that in transformer loop in loop out. So basically that current will be adding. Now I have just selected MV station 1 to MV station 2. Now you can see that I have selected the current should be 125.41, this one, above one. Okay. Now, when this cable is going from MV station 2 to MV station 3, here two MV station will be connected in parallel. So that is why their current should be multiple with the 2. Here MV station 3 to the indoor switch gear of the substation. So here is the one feeder. One feeder mean that the loop in loop and out transformer, and that they travel the power from one feeder. So that is why they we multiply with the 3, because here the 3 transformer will be connected in parallel. So in green you can see that we have MV station 21 to 17. It 125. From 17 to 30, 13 it should be 2, multiple of the 2 1. And then 13 to 14 is become multiple of a 3. And then 14 to indoor switch. Again, fourth transformer will be added. So here we have to apply multiple of the 4 1. So how we will calculate this current? It is that the process. Now again, this is the soil thermal resistivity factor, and this is the circuit diagram. Here I have just dropped down this one because I have just multiplied with that current with stand value. So here is the basically uh, MV cable has some criteria, some criteria. They basically withstand the short circuit current for some seconds, like they have 22 kV KA ampere current, like you have selected the 240 ampere cable, and they have 22.56 KA for 1 second. For 1 second, they have the capability for 1 second they can bear that current, and then fault KA. Okay, okay, okay. So the total derating this value. Circuit one we have basically why we have selected this one. When we selected this one circuit, they basically they select point this one and point this derating. This is basically the derating of that 3 1 circuit one. Okay, and then we have multiply with that soiling thermal resistivity value, and we get that derating factors, total derating factors. And then we have multiply with that the ampacity of the cable with that derated value, and then we get the derated ampacity. Then cable runs per phase, same one like previous class I have just explained that one. How we will calculate? We just divide that the derated ampacity with the load current this one, load current. Okay. Sorry, the load current should be divided with the derated ampacity. We get the number of runs per phase. So here we just, because the derated ampacity should be higher than that one, the load current. So that is why they will increase the number of runs per phase. Here you can see that we have the load current this 376.22 and our derated ampacity 321 second. So here you can see that our derated ampacity will be decreased that one. So here the cable runs will increase to the 2, not 1. Okay. Now the derated ampacity after number of runs per phase. Here basically I have multiplied in two columns and we get that value. And that then spare ampacity of the cables. Here we have just 1 divided by that derated ampacity divided, sorry, G13. G13 means the total current. So here is the derated ampacity of the cables, and this is the current will flowing through that cable. So we just have to get the percentage how much cable will be spare, how much they have the more capacity to bear that current. Like we have the derated ampacity of the 318. They can bear up to the 318 ampere current, but only the 125 ampere current is passing through that cable. So mean that 65.5 5% cable will be enough, and will be having the more capacity than spare capacity they have. So the length of the cable, I have mentioned that one, and then R and X value, then the power loss, same like that. Same like here, G13. G means that this one, the I square R, R. Basically, uh, that R should be uh, ohm per kilometer, ohm per kilometer. So that is why we multiply with the 1,000 and then multiply with the length. So we get the R value. I square R, power loss formula we have used. I square R, that is the power loss formula. And then we get the voltage drop, that is one, uh, square root of 3 I L, then R cos theta, X sin theta, and then 1,000 divided by number of runs per phase. And then the voltage drop percentage, that voltage drop divided by the system voltage 33,000. So that is why we just get that voltage drops. So in tomorrow class, I will be showing again, I will show you something like on the Google MV cable, MV cable, cable. Like here, this is the MV cables. This is the MV conductor, this one. Okay. And then this is black one, this black one, inner semiconductive layer. And then this white one, the insulation, like XLP, we have used that one mostly. Then the auto semiconductive layer, this one. And then the grounding sheath, metallic sheath, this one, sorry, this copper one. Okay. And then we have this armoring of that cable, and then outer sheath jacket. So that is the cable specification. So when we have to size, or we have to check, we have to know about that cables. Outer jacket, then armoring. Armoring means that the protection, like this type of protection, like you can see that some cables they have aluminium armoring. They have aluminium wire, non-magnetic steel wire. So that is why that is called the armoring of the cables. Then the copper conductor, then XLP insulation, then warning tape, wrapping tape, sorry. Then inner sheath PVC, then the non-magnetic armoring, and then outer sheath PVC. So that is basically for the MV cables. Yes, for the MV cable, like here. But for the MV cable sheathing, they are not available. Like okay. So basically, they have this type of the MV cables and looping. I have just explained to both of you. And I think I just you have any more question you can ask, and I will show you, send you the catalog and other things in the group by tomorrow. Mr. Amar, you will message me, or Mr. Kazi, from both of you, anyone can message me for that data, because if I get forget that one, If I remember, I will share in the group. But you have just send me one message for the reminder. Okay. Okay, guys.
Okay, sir. Thank you.
Thank you. Any question?
No, sir. Uh,
Thank you.
I got some
Okay.
superficial idea, and I think that's enough for me.
Okay. 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 Uh, yes, Amar. Are you satisfied, Mr. Kazi? Are you satisfied with the course?
Yes, sir. Yes, sir. To be honest, I don't need to know more details. I just came
Okay.
here to know about to do the business. My engineer will take care of this.
Okay, okay. You basically you are a businessman. I'm a technical person. I'm just doing my small business, like doing the service of that designing. Basically, previous days I am providing that services to the single persons. Now I have shift to one company. I'm providing that service to one company these days.
We are also happy if we can work with you in some projects, and if we can, we will try to afford you.
Okay, okay, no issue, no issue. Yes, Amar, have you any question?
सर yesterday जो आपने आईएसी की जो डॉक्यूमेंट्स भेजे थे वो तो उसमें लिंक चाइनीज में थी, मैं ट्रांसलेट किया, लेकिन वो आईएसी की तो उसमें कोई डॉक्यूमेंट मुझे नजर नहीं आया।
Okay, wait a moment. I'm just showing you. Hmm. Here is the doc 88. Okay, just showing you. Okay, so just you have to click on that. Okay, so you just search there. You just search there. Like I have mentioned IEC 62738. Okay, search that one. Click on the English. Okay, English. And you just see that the updated one should be the 218. Okay, click on the English. Okay, go down, go down. They will be like uh, here you can see that continue reading. Okay, continue reading. Just click on that and that loading the pages. I just have weak internet at that moment. I think when you see that you will read the documents. You read the IC standard. Now I think you
ओके,
should understand.
ओके,
Okay. Oh,
यस सर।
okay. Okay. Thank you. Any other point?
Sir, I
Okay.
want to discuss on another thing that the distribution company installs their meter in which level? Is it in the user level or in 11 kV or in the LV level, low voltage level or medium voltage level?
Basically, at the small houses or corporate sectors, they will install the meters at the low voltage side. because they provide the energy at the low voltage levels. But at some industries like the paper industries and other things where they have the heavy machinery available there. So in that industries, they install the uh, meter at 11 kV.
Okay, that's why we are learning about MB cables.
Yes. But if I talk about the large scale project, like uh, in that we don't have to mention the meters. They have large scale metering panels like that one, where we have to measure the energy number, the performance, and other things. We install the CTs, current transformer and voltage transformer. But in the small residential side here, we have just installed the energy meters.
Okay, okay.
Okay.
सर
Yes.
सर जब हम बात करते हैं फॉल्ट करंट की, तो उसमें तो हमारा जो एक फॉल्ट आता है, तो उसमें तो मेगा वोल्ट में तो मेगा वोल्ट में आते हैं ना, तो उसमें इम्पीडेंस भी तो हमारी इंक्लूड होगी, अगर फैक्टर्स हमें अगर देखनी हो, तो इम्पीडेंस भी तो इसमें होगी ना सर, कितनी परसेंट
Basically,
इम्पीडेंस होगी?
brother, basically, when we talk about the fault, basically it is the fault current which damage the equipments. Fault current. Okay. So when we get that fault current, how we will calculate that one? Basically, the transformer power and their zero impedance through that one. I will share in the group by tomorrow their calculation, how we will calculate that one. uh, I'm just missing something, some points in which that is why I just shifting to the tomorrow. Mm, I have to just check my some documents and then I will send the group. So the power divided by that impedance, basically that will give us the current value. And that current should be the fault current, which travel through the MV cable. But I will check again and send in the group. Okay.
और सर ओके सर, और आपने एमवी स्टेशन की बात की, एमवी स्टेशन 1, एमवी स्टेशन 2, दैट इज शो ट्रांसफार्मर और इन्वर्टर?
Yes, transformer. Basically, when we talk about the large scale projects where we using the MV cables, mostly in Pakistan, you have seen that if we install the 1 megawatt, 2 megawatt, in some cases we have to install terminate that megawatts like 1, 2, 3 megawatt to the 11 kV. So here we just connect all the transform all the inverters. Like we have 10 inverters, like 1 megawatt, 10 inverters of 100 kilowatt. So we have just installed that inverters, and their output cable should be terminated on the one's LV switch gear. We just make one panels in which 11 or 10 breakers are installed, and then we install the one bus bar, and from that bus bar we connect one output breaker like ACB, uh, 300, 400 ampere breaker ACB. And that from that one cable will be going out and terminated on the input of the input primary side of the transformer, and they will step up to the 11 kV, and then their output cables should be connected to the MV switch gear, where we have installed the 630 SF6 breakers, and then bus bar and the CTs and other things will be installed in that panels. And from that panels, the cable will be going to the termination point, that called the MV cables. But in case of the large scale project, we have multiple number of transformer in the field, and then we have main substation available there. Like we have 100 megawatt system. In 100 megawatt, we have like 6 megawatt, 6 MVA, 7 MVA, 3.3 MVA transformer in the field. Then we have to loop in, loop out that transformer, and then prepare one, two, three, four feeders cables, and then we
ये
terminate to the substation there, and we have installed the MV panel there. Again, we install that MV panels, then terminate that cable to the MV panels at the substation level, and then from there one output panel will be installed that will convert like the same one, like in the LV side we have one panels there, 11 breakers there, and then output breaker. So in case of MV we have separate MV panels. For one feeder we have one MV panel, and then that MV like 3 to 4 MV panels, and then we convert into the one MV panels through the converted connected to the bus bar sizing, and then their output should be terminated to the main transformer. That will step up the voltage to the 132 kV, and then from that one we just connected the gantries, and then we do the POC point of connections. So that is basically the flow chart and the block diagram of that.
सर जैसे आपने अभी कहा कि लूप इन और लूप आउट, क्या ये हमारे इनपुट और आउटपुट को शो करता है? थोड़ा सा ये भी
Yes,
बता दें।
yes, yes.
और
Basically, the transformer or MV panels. MV panels has two options. One is input option and the other is output option. So one transformer output cable will be terminated to the input of that transformer. Like I have shown in the block diagram in the net. I have selected the one input output cable of that will be connected to the input of that another transformer, and then their output cable should be terminated to the input of that another transformer, like the third one. So that is called the loop in, sorry, loop out, then loop into the another transformer, then loop out to and then loop into the another term. So that is why called output to input, then output to the input.
सर जो उनकी हमारी जो उनकी एक एक हम जो रखेंगे, जैसे आपने कहा कि उसको पैरेलल में, उस पैरेलल में तो ओके ये हमारा करंट एडअप हो रहा है, लेकिन क्यों सिर्फ एक को हम पैरेलल रखेंगे या एक से मोर देन वन? इसमें भी जो मुझे थोड़ा समझ नहीं आया था कि आपने कहा कि इस वन ट्रांसफार्मर को हम पैरेलल रखेंगे क्योंकि करंट में हमें एडअप करना है।
Basically, when we connect that into the parallel scheme means that there like one they are connected output input at the same level. So basically, loop in loop out criteria is same because their current should be adding. Okay, but how we will calculate how many number of panels or how many number of transformer connected in that one, like two, three, one. Like we have one, then we have two. I just explain in that word, like we get the output cable from one transformer and then connect it to the input of another transformer, like the similar one. I will show you how will I have some.
सर
So
सर इनकी एसएलडी भी हो सकती है ना सर? एसएलडी में अगर
yes,
हमें वाजे
yes, yes. Okay, wait a moment. Oh, wait a moment. I'm just searching out another thing. Right. Okay. Can you see that one? So here is the 1 MV station. That is called 1 MV station. Like this is this box. Because in the large scale project, we just have containerized solution. Containerized solution means that they have LV switch gear, then transformer, then MV transformer in one container. So you have seen in the Huawei and other things, if you have seen already. Have you seen?
Sir, not in
Have you
real, not in real, like online. Hmm, net.
net related data? I think if I have just checking if I have available at that time. Like no, is available at that time. I will show you. Mm, this one. So here you can see that this is basically one MV station in which the transformer and the MV switchgear, LV switchgear in the same container. Okay, this type of. So you can see that their circuit breaker, then transformer, then MV switchgear. Okay, this type of container solution will be used in the large scale project 100 megawatt. So here above one is the one container. Okay, in which this is the LV side. So here we have installed like how many like 11 inverters, 11 inverters. Okay, they have individual breakers. Okay, you can see that they have individual breakers, and their output breaker, one output breaker like ACB 2900 ampere 50 km, and then SPD available, and this is the auxiliary side of that transformer. Okay, then we have the transformer. They will step up that transformer from 0.8 to 33 kV. Okay. At 33 side, we have seen that we have lights, then we have the surge arrestor, we have CT, we have earth switch, then VCB. We have see that we have VCB, vacuum circuit breaker. And then we have at the output bar, that is the bus bar, 33 kV bus bar. We have two terminals. We have two terminal. Two terminal means this is the input terminal and this is the output terminal. Okay, this is the output terminal. So here the output terminal should be connected to the input terminal of that parallel MV transformer. Here we have 11 transformer inverter in that. We have again the transformer, we have that bus bar, and we connect both into that one. Okay, now from that output, so again we have connected to the simultaneously that input. Okay, so here we have connected that one. So you can see that their input one end should be at the same level. So here from that output cable should be terminated to the, this is the bus bar. This is basically the MV substation switch MV panels. Here we have terminated that cable feeders. Again here we have another feeder. Like we have this transformer connected to the output that, and then their output should be connected to the input of that, and their output should be connected to the that panel, MV panel. So here we have two MV panel, and then their output bus bar, and then their output panels, and they connected to the transformer, their earth transformer, and then the POC connection. So in that way, we will connect in the large scale projects. Now it's clear, Mark.
Yes, sir.
Are you satisfied at that moment?
Yes, sir, I'm satisfied. Some things are new, so जैसे सर मेरे लिए
Yes,
थोड़ा सा
yes.
न्यू भी है लार्ज स्केल की, क्योंकि हम तो रेजिडेंशियल इन्वर्टर्स पे काम करते हैं या बैटरीज पे काम करते हैं, इतने बड़े प्रोजेक्ट्स पे काम, क्योंकि अब मेरे भी बिगनर है इस लेवल पे, क्योंकि हमारे उसमें भी लार्ज स्केल पे जा रहे हैं। पीसीएस हो गया, जैसे आपको मैंने पहले भी बताया था, पीसीएस एसटीएस इस चीज़ों पे जा रहे हैं।
So
तो
ये STS है. This is the STS one. So you can call it as STS, one transformer. This is basically
ओके,
STS.
ओ,
Okay,
ओके, या,
okay. Now
यस,
I think you have should clear that this is basically one STS. I will mark a block one. This is basically STS, one STS. You can see in the Huawei STS, you have the LV switchgear in the 11 or 22 breakers, available, then their main breakers available, then transformer, then MV transformer available, and their two output terminals. So this is called the STS. Are you okay? I will close that one, or you have any other questions? Amar,
Oh, हाँ, thank you. Sir,
are
okay,
you
thank
clear?
you.
Okay, thank you. Thank you. Okay, guys. Allah Hafiz. We will meet again by tomorrow.